Hello and welcome to the C Security 102 lecture with the Offensive Computer Security OpenCourseware in 2015. My name is Owen Redwood. This is part of the lectures hosted at hackallthethings.com. And this time we're going to cover heap bugs, format string vulnerabilities, and race condition bugs. To cover heap bugs, we're going to go into dynamic memory management, how it works in C. We're going to touch some aspects of C++ too. We're going to cover the main culprits of heap vulnerabilities, use after free bugs, double free bugs, and buffer overflows on the heap. And we're going to dive in a little deeper than we've done with other topics so far on how these are exploited, because it's very important to get these fundamentals under your belt starting off. These are things that most people don't understand. We're going to cover the case of DL Malik, or Doug Lee's memory allocator, for the purpose and scope of these bugs. And the C standard provides four main ways to allocate memory. To do dynamic memory allocation. The famous one that everyone should know is malloc. It simply takes in a size of a memory space you would like to allocate and returns a pointer to a chunk at least that size. It's usually at least 16 bytes larger or so to incorporate in the heap metadata and header and footer tags, depending on the allocation scheme. There's another one that's less known, is aligned alloc, and that pertains to memory alignment, which is irrelevant on most modern platforms, as processors have been designed to accommodate for when memory alignment issues occur. So most programmers do not need to be concerned with such issues. It's more relevant for embedded platforms and legacy systems. Realloc will take a memory chunk and try to expand or contract it to the new size, and the contents up to that point will be unchanged. The remainder of the chunk will be attempted to be freed if there's multiple for that. Calloc, or calloc, will attempt to perform the same as malloc and also zero out that memory. And by zero out, it means setting every byte to 0. So memory alignment was a processor requirement back in the 90s in most Unix systems, and it effectively means that all the instructions and data have to start on, if you model everything in memory for a 32-bit system, you have byte 0, 1, 2, 3 through 7. Everything should be aligned on the 0th byte for, say, a 32-bit integer. And for shorts, they should be aligned on the 0th or 4th byte. And for bytes themselves, well, it doesn't matter at that point. But you kind of understand, it's pretty self-explanatory. This is a issue that comes up in some cases for attackers during exploitation. If you have your data allocated, your payload allocated on the stack or the heap, and it's not allocated just right, the processor, depending on the platform, may bitch upon trying to land that exploit, which is just interesting nuance. There's another allocation function that uses the stack instead for dynamic memory allocation. It's found in BSD and also is recognized by the GCC compiler and some other Linux distros, but it's not C99 standard or POSIX function, and it is noteworthy because it can cause a stack overflow, and can result in a stack overflow if any of the buffers used in that heap chunk are buffer overflowed. But I digress. So we're going to cover some basic cases like initialization errors, failure to return, failure to check return values, and dereferencing null pointers. Before we cover use after free, buffer overflow and double free bugs. Pardon the slide, it's a little out of date, but the rest is up to date. So initialization errors is simply a developer's failure to initialize an object that has been allocated in dynamic memory, i.e. the heap, before using it. Perhaps they falsely assumed that malloc would zero things out, and this could be either directly exploitable in some cases to corrupt memory logic, or could be indirectly exploitable in the cases that it allows an attacker to see the contents of memory. In other words, this is considered an information leak vulnerability in such a case. Now, the other simple case is when they call one of these dynamic memory management functions and don't bother to check the return values. It can be exploited to cause the program to crash when memory is exhausted, or that heap chunk has been fully allocated for all the bins have been taken up. And in general, if these return a null pointer and then is used to perhaps in a dereference as a function pointer, then it's especially bad. Memory leaks are another simple case. This is basically the developers do not free the memory that they allocate. You can track this down with tools like Valgrind. It's very simple to use. You just type Valgrind in the function, the binary name with all the inputs you give it, and it's very helpful for tracking down memory leaks. These really just result in the end of the day in denial of service vulnerabilities when they crash from memory exhaustion, and that's about it. So we're going to learn more about how memory allocation works on most systems before diving into the other more serious bugs that require this understanding to learn about. And this is how memory allocation works. In general, you have a list or multiple lists of free available memory, and by that I mean memory that is in the segment for the heap is sliced up ahead of time. There are multiple types of slices. Each is of a specific size, and the compiler ahead of time determines these sizes. Typically, it's something hard-coded like 16-byte chunks, 32-byte chunks, 64-byte chunks, 128, 512, multiples of 2 in general. But it can vary. And so when malloc is called and someone wants to allocate something for an 18-byte object, well, it's going to fit it to the first available and best fit chunk. So the memory in the heap is sliced up with a number of slices for each chunk size. And if something takes multiple contiguous chunks, or as the algorithm decides to split an object over multiple chunks, then they are allocated in a manner that is has them all contiguous. All of them are adjacent, and it's all just merged into one fat chunk. It depends on the allocation scheme itself. Now, finally, the third requirement for memory allocation is a means to, when you're done with a chunk, to free it. So at the end you have two lists, one for all of the allocated chunks and one for all of the free available unallocated chunks. Now, not all algorithms actually have a list or a object to manage all of the allocated chunks. Usually that is done in C by the programmer. They allocate something, they get a pointer returned to access that object, and then they free that pointer when they are done with it. but I digress. Um, Typically, when malloc is called, a chunk will be created that looks like this. There's some metadata at the head of it called the header. There's the chunk itself. The pointer will point to here, to the 0th byte of where the data should be written. And then there's data, metadata at the end, the footer. These are called tags. And these tags contain metadata such as the size of this given chunk, pointer to the next chunk, and maybe a pointer to the previous chunk, and maybe some other metadata as well. Typically, there's optimizations made within each memory allocation scheme that makes use of this metadata. And we'll dive into that with dlmalloc in the previous in use bit. So, at compile time, a different memory allocator can be statically linked in. Typically, it's just done dynamically. The linker adds in the code to do this. It's provided by default by the operating system, but each OS may have different memory managers. So, learning today's examples for how dlmalloc works will not translate to how heap bugs manifest on other platforms. And now for use after free vulnerabilities, also known as UAF bugs. These are the most exploitable bugs, probably for the past 10 years or so. They usurped in the statistics stack-based buffer overflow bugs for the top exploited bugs. Anyways, UAF bugs involve the use of any pointer to a piece of memory that has been freed. Once it is freed, it is no longer protected, and it can be overwritten. And the goal of an attacker is to, between the point at which it is freed and the next time it is used, is to repopulate that memory with something malicious. When it's the case of a function pointer or an object that contained a function pointer, the goal for an attacker is to repopulate that memory chunk, and they may have to do that by essentially brute force, or a technique known as heap spraying, which I'll get into in a little bit, to populate that memory. It's not a deterministic process. It's not perfectly reliable, and by the point later where it is used again, essentially the attacker's hope is that when it's used, it's using the malicious version of that object or that function pointer instead, pointing now to an attacker's shellcode or a ROP chain. So, function pointers are very common in C++, and we're going to talk about C++ and vtables in a few slides. It's a little more tricky in C. It's rather uncommon for function pointers to exist. It depends purely on the application itself. And here's a quick little example. These two lines of code demonstrate a use after free bug. There's not much distance between the free and the use. So this goes through a linked list and keeps iterating through it, setting p equals to the next item in the list, and then freeing it as it goes along. The problem is that after the first free is called, when this is issued again, p equals p sub next, it is using freed memory. The reference, as long as it has to p, as long as it hasn't been corrupted, will still point to an object on the heap that will contain this sub next member to facilitate the rest of this for loop. But if this is, say, a multi-threaded application and multiple threads are sharing P, this would be perhaps a problem. So the safe way to do this is to use a temporary variable and go about it this way. Instead of setting P equals to p sub next, use a temporary variable q. It's rather self-explanatory. So in C++, vtables are a common source, or rather a common target for use after free exploitation. Vtables go by many names depending on how you are taught. It may be known as the dispatch table, virtual method table, or virtual function table. And the compiler will build in a vtable whenever a class contains virtual functions or overrides virtual functions that are inherited from a parent class. So a vtable is useless without something called a vpointer, which points to the base of the vtable, and it's used by offsets from the vpointer to access each virtual function pointer stored inside the vtable. And here's a screenshot of how a vtable would look like in IDA. It would be in read-only data. Sometimes it's not read-only and writable instead, and you can corrupt it, but that's a different case of bugs. And the target for attackers is not this vtable itself. Usually this is something that can be freed. Instead is the vpointer. If this exists inside, say, an object, which is typically the case, and the object has a buffer overflow in it or gets freed and then used later, this can be corrupted by an attacker. In both cases where the vpointer is corrupted, the way to trigger it is to just follow along. In the case with a use after free, it's first freed, then there's a heap spray, then the program uses the corrupted vpointer. The vpointer would, instead of pointing to this corresponding vtable, would point to something else populated by the attacker, which would have a function pointer to, again, the attacker's shellcode or ROP chain. In other words, that stage of the payload. But I digress. To summarize use after free bugs, it's a very serious vulnerability whenever there's a function pointer involved. And it doesn't just pertain to vtables. It does exist in C, but it's just less common and depends on the application. The exploitation of a UAF bug relies on the reliable ability for an attacker to allocate user input on the heap, which is typically called the art of heap sprays. And there's some very common patterns that are dead giveaways when you're doing forensics or incident response and looking into malware or an attack that does heap spraying. Certain addresses tend to align into a heap pretty well. OC is probably the most infamous one, and there are a number of others, and we may visit that later on. Now for heap-based buffer overflows, which are more complicated than most people understand. It's not as easy as stack-based buffer overflows, where you have the chance as an attacker to directly overwrite the return address and hijack EIP directly. Instead, exploiting this is a bit nuanced and requires understanding exactly how the heap allocators work, at least the heap allocator algorithms to be specific. So, on the left we have an example of what an allocated chunk looks like, which would be the result of calling malloc. You would get a pointer back to right here where data begins. On the right we have an example of what this would look like if it were freed, or originally as part of the free list. With dlmalloc, the sizes of chunks are always even, and so before we go into more details here, what they've decided to do for an optimization is pack in to the least significant bit a flag. It's a Boolean 1-bit flag, and it denotes whether or not the previous chunk is in use. If it's set to 1, then the previous chunk is allocated. If it's set to 0, then the previous chunk is freed. Now, based off that, the first row also corresponds to this. If it's in use, then the last 4 bytes of user data are repeated in this first row for whatever reason I don't really know, nor do I care. It doesn't really affect exploitation, so I don't care to know it. And if it's freed, then it denotes the size of the previous freed chunk. And so some may consider this first row the tail end metadata or the footer metadata for the chunk. Other people consider it part of the header. This is simply the way that the Secure C and C++ book by Robert Secord teaches it, so I'm just maintaining consistency since I cite it. So, for a free chunk, instead of having data here, the first row of the data section would contain a pointer to the next chunk, and the next row would have a pointer backwards. And this is how it facilitates a doubly linked list along the free list. Now, this previous in-use bit flag is used whenever something is freed, and whenever something is allocated. It likes to tidy up the heap, if you will, and allocate and free things in a contiguous manner. So if things are freed and they're next to each other, then they're coalesced sometimes into a single bin if the algorithms decide to do so. Anyways, so this slide is just there for recap, and for people who don't have the video, it's a bit redundant, so I'm going to move on. Now, this demonstrates exactly where the pointers are going to point. I did say some consider this the first row, but technically the first row of the chunk is the row that contains the size of the previous if it's freed, or the last 4 bytes of the previous chunk if it's allocated. That is exactly where the forward pointers will point, and I think the backward pointers point there as well. So this may be incorrect. This is just simply demonstrating how this doubly linked list would work. Now, here is a set of slides that demonstrates exactly how the malloc process would work. There is a macro that's 4 lines of code that is called the unlink macro. It takes a pointer to a chunk, a backwards pointer that's unused so far, and a forward pointer that's just temporary so far. And what it's going to do, it's going to take a chunk from the free list. It's going to redirect these pointers so it no longer includes this chunk, since it's going to be allocated, and perform the unlinking. So let's say that this chunk, from the size of here to the end, is P. And we're going to move this from the free list to be used, and we have to redirect the forward pointer here and the backwards pointer here. So the first line of code that's going to run is going to access P sub FD, the forward pointer here, and save that to this temporary variable FD. Similarly, we're going to do the same for the BK pointer to store whatever the previous chunk is going to be. So now we have BK pointing here and FD pointing here. Now we're going to go to the next pointer, the next free chunk, redirect its backwards pointer to point to BK, and go backwards and redirect its forward pointer to point to FD. Thus, this is completed, and now it is unlinked, and it is ready to be returned to the user for use. So, here's the things to note. All that changed here were really 2 pointers. The previous chunk's forward pointer and the next chunk's backwards pointer. So, this 4-line macro trusts that the data here in these pointers is correct and hasn't been messed with. Now, what messes this up are any buffer overflows, say in the previous chunks going forward, overriding all of this metadata and messing with these. In order for it to corrupt this algorithm, it would, again, have to be unlinked, or the unlink algorithm would have to be triggered to engage in this swapping process and unlinking. So free is kind of the reverse of this process. It finds the forward pointer and the backward pointer of the adjacent chunks, redirects it to put this back into the free list, and ties these pointers to point forward and backwards correspondingly. Double free, which we'll cover in a little bit, messes up this process, and it is sometimes exploitable. So this is very important to understand, because the majority of buffer overflows have been on the heap since the mid 2000s, and devs just don't understand it very well, so it kind of goes more uncaught than stack-based exploitation or stack-based buffer overflows. So again, the goal for an attacker here is to overwrite by buffer overflow these pointers. And so what essentially is happening in the unlink algorithm is that it's taking a pointer, a destination pointer that's controlled by an attacker, and populating it with the value for a pointer also controlled by the attacker. The end result is something that we call technically an arbitrary write. So the attacker would want to point to some critical part of memory, which would hopefully lead to hijacking EIP, and then pointing EIP to a payload or something else malicious. So I have some slides that demonstrate it step by step, and let's go through them. And for this, we're going to use this friendly guy on the right. He really likes free, and he likes heaps, and we have this code on the left, and it's going to malloc these three chunk sizes, 12 and 666. And the chunk sizes don't really matter here. It could all be 12 just for the sake of demonstration, but I digress. Here we have a basic, let's go back. We have a basic buffer overflow with a unsafe stir copy, just to demonstrate how this works. It's going to use the first pointer, which is going to point here, and it allows the attacker or the user to input their data. Writing towards higher memory would go this way. Afterwards, the first free would be called, and whenever free is called, it does the following pseudocode. If the next one is not in use, then consolidate these two chunks together and merge them into the free list. Otherwise, just unlink it, or perform the reverse of the unlink algorithm, put it back into the free list, merge it back into the free list. And so this is exactly how it uses that previous in use flag. It will go from the first chunk forward twice to use the previous in use flag here to check if the previous one is in use. It's a bit backwards. It's a stupid optimization, in my opinion. It could have been done much more elegantly, but this is how dlmalloc implemented it. That is what we're going to be targeting in this example. When the buffer overflow happens, it will begin here at this row and work towards higher memory. So we will only be able to hit the second size row here and be able to affect this in the second chunk. The first chunk, you won't be able to touch the metadata. So it relies on having adjacent chunks that are all allocated together. So for an example, we have William Wallace here, and he wants to give this program a shit ton of freedom. Now, obviously, the heap metadata on the other chunks is going to get corrupted, and when it goes to free the second, or probably the first, it's going to cause a seg fault. Now, if we give it something more intelligent, and bear with me as I explain each aspect of this exploit, going down to the malicious BK pointer here, and up to the freedom. This is how it would roughly work. Now, the next chunk would be recognized as here, with this size of chunk here, and this is showing off another aspect of dlmalloc that can be abused, in that it allowed signed sizes. God knows why, but this is a valid exploit. Another way to do this is just to keep overwriting into the third chunk, and the purpose of this is to trigger that coalescing algorithm by convincing it when it goes forward twice to check if the next one is in use, by checking the previous in use bit flag, that it will see, oh hey, I want to free this first one, and it looks like the next one is free as well, so I'm going to coalesce them. That will trigger the unlink algorithm, and it will be hijacked by the attacker with these malicious pointers. So, to walk through it, the first chunk is here, the second chunk is here, and the third dummy chunk is here. It believes this because it's using the size metadata to calculate this, and it allows a signed size for whatever damn reason. I think it's been fixed in modern implementations of dlmalloc. But this was interesting bug in the original implementations. Anyways, I digress. So, when free first gets here to the third chunk, it's going to see, hey, the next one's not in use, so I'm going to trigger this unlink algorithm to coalesce them. And so, to walk through exactly how that works, the first line of the unlink algorithm is going to store the forward pointer in FD. The second line is going to store the back pointer in BK. Then it's going to use these to perform the arbitrary write. And the malicious FD pointer, this row is going to be the destination of the arbitrary write. And the malicious BK pointer, the second row, is going to be the value that we write. So, technically, it's going to go to this member of the heap object. So it's going to go to the forward pointer plus an offset of 12. So 1, 2, 3 times 4 for the size of a 32-bit integer would be where it begins, and to overwrite the back pointer for the next one. And so it will also mess up, perform an arbitrary write in the converse case for setting the back pointer, the previous chunk's forward pointer, but as long as the value that is being overwritten here is still a valid pointer, this will not segfault, and it will all run cleanly and allow for you to overwrite an arbitrary 32-bit value either on the stack or somewhere else in memory. Another target other than stack would be the global offset table, overwriting a pointer to a function there to instead something provided by the attacker. And we'll dive into it in the homeworks when we get to the exploitation lectures. Now for the double free vulnerability slides. This occurs when there's multiple frees occurring on the same piece of memory. A very common case is just developer copy-pasta mistakes or copy-paste mistakes. Here you see free X occurring twice when Y is being used in this code. That's one such example. Sloppy error handling is another case. The result is that it can corrupt the heap memory manager, and it can lead to memory corruption crashes and potentially memory leakage. When it is a vulnerability, it kind of turns the free list into a zombie list that's all messed up and barely working. But there are two tight conditions that must exist for this bug case to actually manifest as a vulnerability. First, the chunk that is going to be double freed must be isolated. There must be no adjacent chunks next to it that are also freed. Everything around it must be in use. Second, the destination free list must be empty. That means that free list for that bin size must have every single bin allocated. There can be no free bins. In this case, it's a bit more complicated to exploit and to understand. The secure coding in C and C++ offers a great discussion into the particulars of this a little more deeper. We're going to go through it in some slides, and it's important to note that it affects dlmalloc and some old versions of Windows RTL heap. Most modern allocator alternatives do safe unlinking that prevents double free exploitation. However, you can still exploit this today on modern Linux systems. It just depends on the allocator being used. So the free list would have the beginning node, which isn't a chunk in itself, being self-referential. It points to itself, and there's no empty bins that it can unlink to provide to a malloc call. Now, when the first free is called on the pointer in question, everything goes as normal. The forward pointer and the back pointer both point to this new only free chunk, and the pointers for it, both going forward and backwards, also point to the managing node. And this is, again, the expected behavior. A second free at this point will corrupt the structure. The forward and back pointers of the singular bin will point back to itself and become self-referential. Now, additional calls to malloc or other heap allocation functions will actually keep returning the same bin over and over, and that's because the unlink macro will fail at this point. If this metadata can be corrupted, the unlink macro can then be exploited, and that may be allowed by using some of these malloc bins to write to this data, then calling either a free or another malloc. At this point will both trigger the calling of the unlink macro, which will allow for the arbitrary 4-byte memory overwrite. However, the upgrade for the unlink macro, deemed the safe unlink macro, was added around glibc 2.3, and that was around 2004, so it's for over 10 years now this technique is obsolete. But it is very important to cover for beginners because it shows the depth that attackers have to go to exploit some styles of heap vulnerabilities. Obviously, the easiest ones to exploit are use after freeze. And if we go backwards, this also allows for the corruption, just general corruption of other heap data still. If the heap does get put into this state, you can overwrite other function pointers and trigger a use after free or a buffer overflow situation, similar to the other examples that we've covered so far. Essentially, the heap is used for multiple types of information. Some of it is executable code or function pointers itself, depending on the application. And if you can corrupt these, it allows for exploitation in some cases. So the community consensus is that the safe unlink macro is not perfect, though. And the two famous articles covering this
both released on FRAC, um, are the original 2005 Malloc Maleficarium, which dives into the inner workings of Malloc, how it works, how safe unlinking works, and how some cases can still be exploited in the cases that the safe unlink checks doesn't actually look for, and the consequential edge cases that you would have to look for to exploit. Furthermore, there was a follow-up 4 years later because this original one was very theoretical, low on proof of concept, and it was the Malloc Des Maleficarium, specifically in reference to the DES or NX exploit mitigation, how to bypass it. But we're going to cover DES and NX in a later lecture, so save those for later reading. They're absolutely good reads, though. Now for format string security. I highly recommend reading through the textbook for this course, specifically section 352, because it covers this topic very well. And it is one that most people just don't feel like learning or assume that it is totally fixed and non-exploitable problem by now, which is totally incorrect. We're going to cover the problems that occur when using format strings, misusing them, how to exploit them, how to get it to crash, how to get them to, more interestingly now, to leak information and perform other forms of information disclosures about the process itself, which will enable further exploitation. And mitigation techniques, how to prevent these vulnerabilities from arising. So the following are a subset of the functions that take in format strings and produce them to standard out or whatever the output is. There's printf, there's sprintf, snprintf. Not all of these are vulnerable. snprintf is a good case of that, as long as you use them right. So we're going to first cover how functions are called. There's a number of different calling conventions. In the enterprise world, there's 32-bit Linux, 64-bit Linux, and then Windows style, and it differs also for 32 and 64-bit. And in this case, this is 64-bit code. We can see because the registers are RAX, RBP, RSP, so it is 64-bit registers. And in 64-bit Linux, it's going to pass the first n number of arguments in through the registers. Eventually, it will spill over onto the stack because there's a limited amount of registers, and you can theoretically have a unlimited amount of parameters per any format string function. So again, the way functions are called depends on the architecture, depends on the calling standard, which is dictated by the operating system, and also depends on the type of function. Because normal user space libraries differ drastically from, say, operating system call. But we're going to cover that in depth later when we get to the exploitation development lectures. Here we have an example of 32-bit Linux. And we have sprintf to a destination buffer the following format string with the following parameters. We have it colorized here in gcc.godbolt to illustrate exactly what lines of assembly correlate to what lines of source. Some lines of source don't correlate to assembly, and we may cover that more in depth later, but the compiler does this here and there. So what it's doing is moving the arguments of 4, 3, 2, 1 from order of right to left onto the stack. And then it makes the final call to sprintf after loading a destination pointer for the destination buffer. So with 64-bit Linux, the registers are instead used. Starts with R9D, R8D, ECX, EDX, and obviously the compiler jumped from the 64-bit to 32-bit registers for some reason here. Then it loads in a destination pointer for this local stack buffer, and then calls sprintf. If you pass a 64-bit function enough parameters, it will eventually spill over onto the stack. And we see here that it's using 1 through 8, and it's pushing 8, 7, 6, 5 all onto the stack. So after the fourth argument, it will actually use the stack for that parameter, which means that you can still target stack-based variables and pointers, including the return address, with format string exploitation. Now, here's an example of a printf function done properly. There's the format string specified, and then the input to correspond to that conversion specifier. Unsafely is just taking in a destination buffer and printing it. There's nothing preventing this from containing format specifiers itself, and then making the code think to keep looking on the stack to match those conversion specifiers and print them out. But we'll show that off in a little bit. I'm getting ahead of myself. So here are all the flags and conversion specifiers for a format string. The format is that before the conversion specifier, which are listed here, which most people who have programmed C are familiar with, %D, which is for integers, %C for characters, %S for strings, maybe %X for some. But prior to the conversion specifier, between the % and that character, you can have other flags that specify flags specific to that format specifier function or format string function. Flags that denote the width for a numerical output, and we'll cover that in a little bit. Precision to print out floating point decimals. As well as a length modifier flag, which pertains to almost every one of these, which we show on this slide, which has a nice handy chart. We have at the top the specifiers D and I for integers, U, O, X for octal, hex, F, G, A for floating point, hexadecimal floating point, and I forget what G is, but yeah. C is for character, S is for character array, otherwise strings, P is for pointers, and N is for the number of bytes written so far to output, which is a very interesting and useful one for exploitation, as well as %P. Now let's cover how these format string functions are exploited when vulnerable. In the following cases, where they're simply used to process user input, for, say, buffer here without any prior variable passed to specify conversion specifiers, if an attacker instead provides conversion specifiers, it will process them in a vulnerable manner. Now, for this case, with %S's, it's going to pop values off the stack and treat each one as a pointer, trying to read a string at the value at the destination of each pointer, and it will keep going, matching each one until all of the %S conversion specifiers are satisfied, or until an invalid pointer is dereferenced and cause a segfault due to an access violation. Here's another example exploiting printf with the hex format conversion specifiers and specifying a width. This will move forward on the stack an amount that corresponds to the default length of the %x or the given conversion specifier and will expand or contract it to fit within the given length or width. Um, and by printing it out this way, it makes it very human friendly. If you have spaces or new lines between each one, it's even better. And there's going to be output in it's going to be stored in memory in little endian format on most x86 64 systems. And the endianness of the target platform absolutely matters. Now, the length that it corresponds to by default is given by this top row. So a %x is going to read off a number of bytes on the stack corresponding to an unsigned int, and so on for the rest of these, unless you specify a length specifier that will move the pointer forward by this length amount. Now, if the user input buffer here is stored on the stack, it's going to lead to an interesting case of exploitation that allows the attacker to view arbitrary memory locations. First, the string is affixed with a memory location that the attacker would like to view. Now, it's obviously stored in little endian format, so it's going to be O4E5F5DE. And the attacker here is going to have to play with appending %x's to, you can specify the width to move the variable argument pointer forward until it gets to this point. Then the point of this technique is to correspond this address on the stack with a conversion specifier to dereference it and treat it as a string pointer. So we'll load this, go to the destination that it points to, and print out the memory contents there as if it were a string. Now this will work on 32-bit systems rather reliably, but if the value is stored on the heap, it may not be exploitable depending on how the format string function is implemented. Usually %s corresponds to a value on a stack being treated as a pointer. So again, little background information if this example confuses you. /x denotes an escape character in ASCII encoding, and it is used here to encode the address here, which would otherwise be interpreted as just raw ASCII characters and not work the same way. Each one of these would take up 2 bytes or so, depending on the character width. This is a very common technique in exploitation, and it's one you're going to have to become very comfortable with. So, we've covered reading values, in fact reading specific values at arbitrary locations. How about writing to a memory address? Well, that's where the %n specifier comes in. It is the only specifier that actually results in writing to a memory location, which is quite curious, and its original purpose is quite outdated. And the purpose it serves right now in modern programming is kind of dubious. But I digress. It's there for legacy purposes at the very least, which we all know how that goes. So, %n writes the number of, let's go back. %n writes the number of bytes written so far to a memory address that it will match on the stack, similar to %s in the previous example here. So HELLO is 5 so far, and if we're declaring int I here, it's going to correspond that to this destination, and it's going to write 5 to the variable I. Now, you can use this with the previous technique to move the pointer forward, and as long as this is stored on the stack, you can control the destination of this assignment. Furthermore, by using a width specifier, you can dictate exactly what value to write to this destination pointer. In general, it works very well for small values. Some program constraints make this break or work unreliably for very large values, and sometimes you can write memory addresses. The problem is that on 64-bit systems, many memory addresses require a number of null bytes at the beginning, which becomes tricky when trying to write those out in this format. But if you specify the length modifier, it may constrain the value written at the destination to be within that length. So, if you're trying to write a pointer on the system, a long or a size a pointer type may be the intended maybe the solution for you. Now, the goal would be to craft it in such a way that it has the leading null bytes. You may be able to do that by having it just stay at a low number or wrap it all the way around so it gets truncated down, leaving the most significant bytes as null. However, what matters most if you're trying to write a pointer is the endianness of the target platform. So if it's little endian, again, the least significant byte is going to be first, so it's going to be flipped from what you might from the human-friendly format, which is big endian, where the most significant byte is first in memory. So on most enterprise platforms, Intel, von Neumann, etc., they use little endian, and the goal there, since you have to write something in memory that's little endian, is to use the width specifiers to generate the little endian form of the pointer, instead of calculating the original form of the pointer and then trying to finagle it through multiple format string exploits, which I'm going to show off next, which is demonstrated in the Hacking Art of Exploitation textbook, but I digress. So, on page 174 of the Art of Exploitation textbook, it demonstrates a technique that uses 4 memory overwrites to write a byte each time, striping over 32 bits or 4 bytes in a target destination. The first byte would be to this address 755. Second byte would be 1 byte forward. Third byte would be another byte forward, and so on. This is the hard way to do it, and again, the easier way is to simply calculate how it should look in little endian format and use the width specifiers to generate that number, and then print it to the destination by %n in a single write. And that wraps it up for format strings and brings us to concurrency and race condition vulnerabilities, which summarized very well by this unfortunate train problem and is common in distributed parallel computing. So there are 3 terms that are essential to know: concurrency, multithreading, and parallelism. Concurrency involves several computations executing simultaneously and potentially interacting with each other, maybe sharing memory or objects or etc. This does not always equal multithreading. It is possible actually for multi-threaded application to not be concurrent. But that's not a really big point you need to know. Multi-threading simply means a program that has 2 or more threads that may execute concurrently, but don't necessarily need to. Parallelism, however, relates more towards either a data or a task perspective. For the data parallelism model, the data set is simply split into segments and pushed out perhaps to the cloud, and that's all done in parallel. For a task parallelism model, it is split into several distinct tasks, and they're all run in parallel. These are the three properties necessary for a race condition vulnerability to be present. The first one, obviously, is there must be at least two control flows, either threads or processes or etc., operating concurrently, and there must be a shared object that they are collaborating with or working with, and it must be both accessed and by both of them while they're executing concurrently. And at least one of these processes or threads must alter the state of that object, that shared object. Another important topic or term in type confusion is time of check and time of use. In general, if these two times are not atomically the same, then vulnerabilities almost always arise. Notable examples involve checking whether or not a user has permissions, checking whether or not a file is present, checking whether or not the file has the right permissions. These are all things that can be altered during the time of the race condition to cause the program to operate in an unsafe state. Here is the best example you could possibly learn. The time of check to the time of use for the Rails junction switch here was used in an unsafe way. The train was moving along forwards. Before it got to the juncture, it was checked, is there a train on the juncture right now? No. Some time went by. The train kept moving forward. Then the juncture switched over. At that point, the train had already passed midway over, leading the train to this unsafe state, where if it had gone any further, it would be derailed. So, the concurrency properties are the train and the tracks. They're both running at the same time, doing different things. The train is going forwards, and the tracks is monitoring and also is changing the juncture. The shared object is the juncture, and the state that is changed is the juncture too. Here are some general strategies for bug hunting race conditions. Focus on the shared objects. Race conditions are going to happen there. That's the choke point in the topology of the code. Now, for each shared object, follow through the code. For each fork, process, or thread that may be operating on it. Keep in mind that the operating system may context switch out any thread at any time for another thread to operate. Now, it doesn't really help to build like truth tables to say order of A, B, C, then B, A, C, then C, A, B, C, B, A, B, C, A, etc. It doesn't really work like that because at each line of code there can be a context switch, multiple threads can run and they can return, and the same can happen after that line of code is done. So it becomes unscalable for an approach. So for now, it's kind of more of a manual process. Focus on just where the states change and try to figure out between these state changes and state reads between the threads how things can interact unsafely. So for each state change, enumerate what other concurrent entities might also be operating on it. Hunt for the reads and the writes on it, and that is a general strategy that I've had some success with, just at a high level. Now, go forward slides, come on. The potential results are, obviously, you'll get the classic deadlocks, which result in a denial of service, but you can also get corrupted values, which can lead to undefined behavior, depending on the application's logic. There have been several bugs that have exploited permission talk-to bugs that have led to attackers gaining elevated permissions, i.e. permission escalation, or privilege escalation. And finally, if any shared objects are volatile In other words, because the developer made a mistake or didn't understand the impact of that, these are actually handled in very undefined ways when handled asynchronously because they're stored just in the registers. And so they're hard to sync up. So we've struggled with concurrency for decades, and there's still no standard model for it as far as I know from the last time I took a class on it 4 years ago or so. And development is still very error prone. There's not any that I know of solid debugging tools that work for the general case in this context. And it's hard for programmers to reason about, especially in a bug hunting sense, because as I said, any manual process doesn't really scale well with the number of threads you have. I've had to do bug hunting on something that had 255 threads to find race conditions and memory leaks on it. It took months of my life to do. It was miserable, but at least it paid off. And this is still likely going to be a source of many vulnerabilities in years to come. You can't fuzz for these things. You can't do symbolic execution or any automated vulnerability analysis techniques to discover these things. They kind of just occur. Here are some good resources on general race conditions. The first one is a link to a guide on how to handle race conditions and do shared object interactions safely in the latest C spec, the C11 standard. The second link is a link to general operating system level race conditions, which applies to Linux and Unix systems. This third link is a lecture on exploiting race condition vulnerabilities. And it's pretty interesting as a quick lecture. That concludes this lecture on heap, format string, and race condition vulnerabilities. The following sections of the Hacking Art of Exploitation book are relevant, and at this point you should play around with the quiz on C++ vulnerabilities and bug huntings at q.viva64.com. This is hosted by PVS Studio, the team that puts that together, and they've posted a lot of open source bugs that they found with their code auditing tool. Secondly, you should start homework 2, the homework that corresponds to these lectures. And that wraps it up. Till next time.